Okay, our next speaker is Glenn Pears. Glenn is a graduate of University of Queensland with an MSc from 1997. Since then, he's worked for World Geoscience, Fugro Airborne, Quantec Geoscience, prior to joining Mirror Geoscience in 2003. And at Mirror, Glenn is a principal consultant focused on integrated interpretation and modelling, with a particular emphasis on constrained geophysical inversion. And Glenn also contributes to Mirror's software development. Thanks, Glenn.
Thank you, Peter. Firstly, I'd just like to say thank you for the opportunity to present here today. And I'd also like to say or acknowledge a thanks to my co-authors, James Reed and Tim Chalk from the Mirror Geoscience offices in Australia. The title of my talk is, it's actually evolved a little bit from what's printed in the proceedings there, but it's basically the same concept and theme. The title of the talk is Advances in Geologically Constrained Modelling and Inversion Strategies to Drive Integrated Interpretation in Mineral Exploration. So as a quick outline or overview of my talk, I'm going to discuss the role of geophysical inversion in mineral exploration, constrained inversion and strategies for integrating geology and geophysics. I'm going to demonstrate a case study, and then I'll close with conclusions and acknowledgements. So what's the aim here? What are we trying to do? Exploration is transitioning, typically at depth now, undercover, and requires geophysics. An integrated approach to modelling reduces ambiguity and maximises value from all data sets. Geologically constrained inversion itself is a direct driver for integrating geological and geophysical data. An effective implementation of geologically constrained inversion, which is usually the challenging part, requires an interactive approach between geological and geophysical modelling. So forward modelling and inversion play a major role integrating geological and geophysical data, but there is a diminishing interest in diffuse physical property distributions typical of unconstrained inversions, and there's increasing interest in inversion as an important part of an iterative interpretive process adjusting the geological model. The illustrations shown on the slide on the left show an unconstrained inversion, which we're probably all familiar with seeing, which is typically a smooth, diffuse density anomaly, which is a model that has a computed response that corresponds with the measured gravity data. The constrained inversion process on the right has provided a way to integrate the gravity, the drill hole data, the rock properties, and interpreted sections such that the geophysical data has been interpreted in terms of geological boundaries and domains. Inversion algorithms that operate directly on geological models are a strong driver for integrated interpretation. They offer a variety of inversion styles to begin with. You've got geometric inversion, changing the shapes of domains, or lithology-based property inversion, which can be either homogeneous or heterogeneous within each geological domain. Geological constraints can be imposed directly on geological boundaries in geological models, and rock property constraints can be assigned per cell or per lithology. The most important point is the result is a geological model. We've got a small example of lithology-based inversion on the screen there, where it's just EM inversion, looking at depth of basement, where it's just a simple two-layer model, conductive cover overlying basement, and the output from that is a basement topography surface direct from the model file. So what's the perceptions of geologically constrained inversion? If we consider the intricate-looking machine shown in the slide to be geologically constrained inversion, sometimes the perception is that this elaborate algorithm takes the geological constraints, the raw inputs, such as drill hole data, mapping, rock properties, and the geophysical data sets, and somehow produces a perfect geologically constrained model from these inputs. If only that were the case. No matter what sort of constraints we have, we still need to provide a sensible starting model for geologically constrained inversion. and the importance of actually interpreting your geophysical and geological inputs and developing an understanding of how these different elements will be supported in a 3D model is often overlooked. In fact, a poor starting model can often be the deciding factor as to whether a geologically constrained inversion behaves sensibly or not. There's a simple illustration here which is showing two panels. The upper panel shows the inversion result of a poor starting model compared to the inversion result of a better starting model on the lower panel. The starting model simply contains a lithological contact which has been modelled with different geometry in the two cases. So different dips, slightly different position. The magnetic susceptibility contrast across the contact is the same for both starting models. The result for the better starting model has preserved the integrity of the contact after inversion. This in itself validates the starting model, whereas the poor starting model has attempted to correct for the poorly defined contact, but not necessarily in a geological manner. So what is the strategy for effective geologically constrained inversion? We believe a key strategy for implementing effective geologically constrained inversion is to develop a starting model comprising homogeneous geological domains that explains the majority of the geophysical response when attributed with those homogeneous rock properties for each domain. And to achieve this, we need to identify geological domains that the geophysical data is responding to, and to use geophysical modelling to better define the shape of those individual domains. For example, in the illustration there on the left, we're looking at an image which is an excerpt from the Mount Dore study area in Queensland, Australia. It shows the first vertical derivative of RTP data superimposed over the regional magnetics. When I look at that, the first thing you notice is a lithological change from east to west. So let's incorporate that into our model. With that contact, sorry about that, so on the right-hand side we've got the representation of that contact built into a 3D model there. So the next step, once you've started to think about interpreting your data, is forward modelling and testing different geological elements. This is a fundamental step to developing a good starting model. Forward modelling allows you to test geological ideas before building your possibly complex 3D geological model, which could take time. For example, thinking back to the simple contact model from the previous slide, this has been forward modelled and its computed response is shown in the centre there, next to the measured response on the left-hand side. You're seeing an impression of the background response, which is being reasonably well reproduced there, and it's validating the presence of that geological contact in the model. The slide on the right, or the illustration on the right-hand side, shows the residual, which is then brought to our attention the next two most prominent features to model. And this is part of the process of building up this starting model, assessing your data like this. So again, forward modelling. We've identified two particular features there. You can use forward modelling in a parametric style of inversion, as well as Elliot was just talking about, which allows you to actually start to interpret three-dimensional shapes for these particular domains that are going to explain that magnetic response. Then incorporate all the individual geological elements into a single model and validate that model through forward modelling again. In this case, you can see that no more than 4 well-defined modelled domains explain the measured geophysical response reasonably well. This is a very simple model, but a very good correspondence has been achieved between the observed and calculated data. When running a geologically constrained inversion, it's important to always forward model your start model. It's something that's incredibly overlooked in the industry. It's important to assess the misfit with the measured response and gauge for yourself if you're asking inversion to solve a reasonable problem. It is also important to recognise that the actual methodology can vary considerably. In a data-rich environment, there may be sufficient information to support geological model construction and immediate validation through forward modelling and inversion. In other cases, where subsurface control is limited, a geologically based model can be developed through investigative 3D geological modelling of geophysical data. This was what we just illustrated with that simple 4-unit model. In these scenarios, interpretation does tend to comprise not just one inversion, but many forward modelling and inversions to understand the relationship between geology, geophysics, and rock properties. The general process I've tried to summarise in this flowchart. It emphasises the necessary phase of understanding the relationships between geology, geophysics, and the rock properties, and the investigative modelling exercises that occur to validate these relationships. In turn, these relationships are used to define or update the interpreted geometries for those geological domains before they are incorporated into a detailed 3D model. This interpretation in itself involves many forward modelling runs and inversions. The key point is that by the time you get to the 3D geological model construction phase, the developed understanding results in a 3D geological model that, when attributed with homogeneous rock properties, explains the majority of the geophysical response. Even considering the cases where there is a lot of geological constraint, it is still important not to divorce construction of a geological model from the geophysical data. You do not want to invest large amounts of geological modelling time into a model that will have difficulty fitting the measured responses. After you've done that, the model is then presented to geologically constrained inversion, and having that good starting model better resolves irregularities within the assumed geological framework, which may be relevant for exploration. Those features that are resolved through inversion may be direct targets that you're seeing, or alteration that has a subtle representation in the actual geophysical response. So what I'd like to do is illustrate some elements of this thought process through the Cave Rocks case study. As far as Cave Rocks is concerned, I'd like to acknowledge at the very beginning Goldfields for providing permission for us to use and present this case study here, and also Daniel Eden, formerly of Mira Geoscience, for doing much of the work in this particular case study. The Cave Rocks project area is located in the eastern goldfields of Western Australia. It's a little star marked on the map in the top right of the corner there. It's approximately 12.5 kilometres northwest of Kambalda and is prospective for both nickel and gold mineralisation. The Cave Rocks project is an example of integrating geological and geophysical data. The objective of the project was to produce an integrated 3D geological model based on existing mapping, sparse exploration drilling, and airborne geophysical data. The geological model was constructed and tested against the geophysics, and there was an inconsistency noted. And this inconsistency was resolved, and that change in thinking had a potentially significant impact on the targeting strategy. So as far as the regional geology is concerned, the study area lies within a major north-northwest trending structural corridor, which probably represents a primary syn-extensional rift, into which greenstones were subsequently in place. It's the basal contact of this event which is of particular interest for targeting. In the illustration there, just to highlight some of the key units, you've got the mafics as light green and the ultramafics as purple, and you've got the granitoid in a pinky colour towards the left in particular, and you've got felsic volcanics in yellow and metasediments in grey. Gold deposits are actually shown as yellow squares in the image there. If I just click, you will see the illustration of the regional magnetics, and you can see the magnetics strongly responding to the mafics and ultramafics in the area. In terms of the geophysics that we had to work with, there was a 2007 fixed-wing Falcon survey that was flown. That provided us with the TMI and a sample of the gravity gradient data. The GDD data is shown on the slide there. The survey was flown with north-south flight lines with 100 metre spacing and an 85 metre nominal terrain clearance.
5 minutes.
The other geophysical survey that was available to us was a VTEM survey, which is shown on the right. The Falcon gravity data is shown again just to show the relative amount of coverage between the VTEM and the Falcon coverage there. The VTEM survey was flown at 200 metre line spacing in an east-north-east flight line direction, and the transmitter was at a nominal terrain clearance of 35 metres. Geological maps and interpretations were also provided. The main geological units we've talked about before, but in essence we've got the ultramafics as purple, the mafics is green, and in this case we've got the sediments as grey and the granodiorite in pink. Everything that we see as a light yellow is cover or regolith, so a lot of this work was being done beneath cover. On the right hand side is an interpreted cross-section, and the location of that cross-section is shown as the red line across the left hand side image. And it's indicating that the interpretation in the information that we were provided is illustrating that it's a quite tightly folded anticline in the area there. So with this in mind, interpretation and modelling of geological contacts beneath the cover commenced. We were using the geophysical data and existing mapping, but filling in details and refining the geological contacts from the potential field data. With that updated information, we constructed the geological contact surfaces from the line work and dips and inferred the line work and the dips that were inferred from the cross sections and mapping. We were also able to incorporate a layer of cover into the model, which was derived from the VTEM data, the drill hole data, and outcrop. The illustration shows a map of the cover thickness, and the colour range there, it's a little bit hard to see in the colour bar, is actually 0 metres thickness where it's blue, going to about 50 metres thickness of cover where you've got pink colours there. The key point to highlight here is how we're using information from the different data sets to incorporate into the one model. So the modelled surfaces and cover were combined in a 3D geological block model. They are attributed with homogeneous properties, which were in turn optimised through a geologically constrained homogeneous property inversion, and the computed gravity and magnetic responses were assessed. The three grouped illustrations on the left show the measured Falcon GDD, the calculated GDD, and the residual GDD. The colour ranges for the measured and calculated are plus or minus 80 ertvos. The residual is shown on plus or minus 30 ertvos. What I've highlighted for you in the slide there is the significant positive residual response to the northern part of the survey there. Similarly, if we go to the right-hand side image, there was another curious exaggerated residual in the homogeneous domain geological model response residual as well for the TMI. That started drawing our attention to this particular area where our anticline was actually plunging in one direction, and we were curious to see what was going on. So I don't actually have the actual constrained inversion results for that particular stage of the project, but what I can show you is a north-south section where we've got the white line here of an unconstrained inversion results. And for this particular model, we've got the northern end towards the left and the southern end towards the right. We can see that the anticline is actually plunging towards the south, and both the susceptibility and density results from the unconstrained inversions are immediately suggesting that that's at odds with the current geological interpretation. So, prompted by the difficulty fitting the potential field data, the AEM profile data was revisited and a qualitative interpretation of dips was undertaken based purely on anomaly shape. The outcome of this is shown on the right, where orientated tablets indicate the interpreted dip. Predominantly tablets on the west are dipping towards the east, and tablets in the east are dipping towards the west. By most logical reasoning, that would tend to suggest a syncline more than an anticline. So accordingly, searches were performed for other geological maps and interpretations, and sure enough, a government geological map was found that depicted a syncline over the area of interest rather than the anticline that had initially been represented in the supplied geological sections. So that took us through the process of updating the geological model to be a syncline. Now, as you can imagine, considering that the key aim is attempting to identify the basal contact of the ultramafic, having this significant change in the orientation of the geology would have had a major impact on any targeting strategy or drill hole planning that was going on. So we again went through the process of updating that model, creating that to a block model which could be attributed with homogeneous properties, and then recomputing the forward modelled responses. With limited time, I'm only going to bring you back to their measured and calculated GDD response, but as you can see, overall we're getting a very good comparison, and in particular the amplitudes are very comparable towards the northern end where we had the plunging anticline before, and now we've flipped the direction of that around. So this in itself is a very important step as well, because what we've done is we've created a geological model, I just want to emphasise this point, which has homogeneous domains on it, and just with those homogeneous domains we are reproducing the measured gravity data here very well. So once you've got the model to that particular stage, you can present that model to a geologically constrained inversion, and it will then solve for heterogeneous density variations or heterogeneous susceptibility variations within each of the individual geological domains. And the slide at the moment shows a horizontal slice through each of the density and magnetic susceptibility models. Preservation of the geological domains, as I mentioned in the output model, further validates the geological model, and particularly towards the north where the syncline is plunging. The key outcomes in this case study is integration of geological and geophysical data into one model, and the interpretation process prompted a significant change to the geological model supported by the geophysics, which in turn has implications for targeting. So in conclusion, integrated interpretation minimises ambiguity and maximises return from data sets. Geologically constrained inversion is a direct driver for integrated interpretation, but there needs to be a shift in mindset when it comes to geologically constrained inversions. Integrating geological and geophysical data involves many forward modelling and inversion runs to develop a geological interpretation consistent with the geophysical data. Conclusions 2, geologically constrained inversion is better conditioned if a starting model is developed comprising geological domains that, when attributed with homogeneous rock properties, explains the majority of the geophysical responses. Understanding and utilising the relationships between geology, geophysical responses and rock properties is key. Identify which geological components the various geophysical data are responding to, and then try and infer the geometry of that geology from the respective geophysics. Forward model. Test geological concepts against the geophysics. And finally, resist approaching geological modelling as a distinct, separate component of work from geophysical modelling. That's it. Thank you. Sorry if I overrun.
Yeah, thanks, Glenn. We have time for just one quick question. No? Okay, I think